We're going to cover some graphical fitting methods to be able to fit parameters in this equation, a first order linear system with dead time, or a first order plus dead time system. Now, one of the reasons why this is so important, because if we can calculate Kp, tau p, and theta p, then we have tuning correlations, for example, that will give us Kc, tau I, and tau d, or P, I, and D values for a controller. So if we can characterize our system, then we can come up with suitable guess values for a controller. The other thing that allows us to do is be able to talk intelligently about the dynamics of a system. For example, if you're talking to someone about the response of a manipulated variable to a controlled variable, you might say, well, this has a time constant of about 7 minutes. So that would tell the individual, well, okay, it's going to get about halfway there, or a little more than halfway there, after 7 minutes of time if I give a step input to this. So it allows us to talk about dynamic systems with a common language, and these three parameters are very common. Talking about the gain, the time constant, and the dead time. Okay, in general, we can use a couple different methods. One of the things to note about this method is that it requires a step input or a step change in the input. And if you have something that is like this, okay, there's a lot of steps. You can't necessarily use this method. So it has to be just a single step, like we show here, step up, and then it's held at a certain level. Now, a lot of times you can try to characterize the system if you're running the process. You can do a step response. You can give it a step input. As long as there aren't a lot of other disturbances that are affecting the process, then you can use that data to be able to characterize your system. Okay, so the steps here are 7 steps. First of all, we want to be able to find delta y and delta u, like change in output, change in input. And then we'll calculate our gain. And then we'll go on to calculate our apparent dead time. The next part, these last 3 steps, are just breaking it down to help us find the time constant. Okay, so let's go through this. Now, again, graphical methods, they're not necessarily going to be that exact. We might use something like optimization. We'll be doing later to be able to calculate more of an optimal fit to this. Okay, so here are the 7 steps. Let's just go through this first one with a little bit more detail. Here is my output, and this would be my delta y. So my delta y is going to be 3 minus 0. So I look at my change after a long period of time, and that change is equal to 3. Okay, my delta u, similarly here, I have delta u, and that is going to be equal to 1. So from this, I can calculate my gain. It's 3 divided by 1. That equals 3. Now sometimes there are units associated with this. So let's say this is degrees Celsius, for example, and this might be kilograms per second. Then my gain is going to have units of degrees Celsius divided by kilograms per second. So there are generally units associated with those. It's the change in output over the change in input, and depending on the units, you're going to have a different value. So let's also next find the apparent dead time. One way to do that is to take the tangent to this line coming down where it intersects, and then we're going to look at so we're fitting this exponential decay, and so at this point right here, we're going to then start calculating up and approximating that with a first order system. So there's going to be a little bit of error right here, and we're okay with that because we don't necessarily want to start like here and approximate the system like that. Okay, so we're going to tolerate a little bit of error right in this region by essentially looking at the tangent line here because we are going to be approximating this with an exponential decay to the new steady state. So the dead time is going to be from where the input started to where you meet that starting point of the response. And so we're going to say that this is theta p. And so that is going to be about 1.2. Now this one also has units. I didn't put the time units here, but let's just assume it's going to be in seconds, for example. So that would be 1.2 seconds. So if those time units were in minutes, it'd be 1.2 minutes. Okay, next we're going to try to find the time constant. So we're going to do this one first, this one second, and the last three are this one. So this is maybe the most difficult one to find. It's really not that hard if you just remember these final three steps. So first of all, we're going to just calculate, we have delta y, and we want to calculate delta y times 0.632. Okay, and that's going to be about 1.7 or so. Okay, this is just a graphical method, not very precise, but about 63% of the way there. Okay, and that's where it intersects that line, 1.7, 1.8. Okay, and then what I do is I find the time at which that crosses that threshold. So here's my time here, about 2.9. And just this interval right here, that's going to be my tau p. Now it doesn't include the dead time. So that's one common error, is that a lot of people maybe include that dead time in there, so they'd say, well, my time constant is 1.9 or something like that. In this case, in all cases, you don't include the dead time. It's the response after that apparent dead time. So this one's going to be about 2.9, okay, minus about 2.2. And so that's going to be 0.7. In that case, we'll just say it's seconds. So 0.7 seconds. So the first order linear system that approximates this then is going to be 0.7 seconds times dy dt equals negative y plus 3 times degrees Celsius divided by kilograms per second, okay, times u of t minus 1.2 seconds. So this equation right here will translate into something, and I'll just go ahead and sketch it here, erasing some of this. It'll translate into something that looks like this. Okay, there's the approximation that we have. Let's go on down to the next one. We'll go just a little bit faster on this one. And with each of these, maybe pause the video and try it yourself, and just see how far you can get on your own. Okay, so I'm going to go a little bit faster on this one. Here we have a delta y. Delta y equals negative 3 in this case, and delta u is going to be equal to negative 1. So my gain is going to be negative 3 over negative 1. It's going to be 3 again. Okay, and then I'm going to start here and go out to this tangent of the inflection point. Okay, and my apparent dead time, okay, again is right here. And so that's going to be about 1.2 seconds for theta p. Okay, I've got 63% of the way there. And about here. Okay, I'll draw the line over. And where that intersects is about here, 2.9 or 3. And so this is going to be tau p. And tau p is going to be about 0.7 seconds again. Okay, so this is actually the very same system as we had before. We had this same equation. Okay, even though the response looks a little bit different, it was just a little bit of a trick there to see if you could recognize that this is actually the same system. It's just that we gave it a negative step here on the input and it made it look different, but we're still able to calculate about the same response. Okay, let's go on to problem number 3. Okay, we can see it asymptotically approaches 10, or actually this is going to be 10 minus 5. Delta y equals 10 minus 5, and so delta y equals 5, and delta u equals -1. So my gain is going to be delta y over delta u. In that case, it's going to be 5 divided by -1. I have a gain of -5. Let's go and look at the tangent to the inflection point. And it starts right here and comes out. Okay, and so that gives us a dead time, an apparent dead time of about 0.9 seconds. Yeah, I'm just assuming this is in seconds even though it's not labeled. Okay, after that I need to find about 63% of the way there. So it's not 63% of 10, it's actually 63% of the change. So this is going to be delta y equals 5, and I'll multiply by 0.63 times delta y. Okay, 0.63. 2. Alright, and that is, I don't know, about right here. I'm not going to be very precise with this. Graphical fitting methods, you don't necessarily need to be very precise. There's my time, about 4. And so tau p equals 2.1 seconds. Okay, so I have an approximation of kp, theta p, and tau p. And then I just plug it back into that equation that I showed you before. Minus y plus k times u t minus theta p. Okay, and then you'd have your first order linear system. Okay, let's go on to problem number 4. Okay, this one has a bit more dead time. Okay, delta y. Yeah, you should be getting pretty fast at these. That's going to be equal to delta y equals 10. Didn't write that y very well. Okay, and delta u is going to be equal to 5. So my gain is equal to delta y over delta u, and that equals 10 divided by 5, and that's 2. Okay, let's look at the tangent to this inflection point. Right here, I'll draw it right down like that. Okay, intersects with 2. My step change happened right here. So there's my theta p. Theta p is going to be about 1.5. And if there were time units there, it'd be like something like seconds. Okay, let's look at about 63% of the way there. I'm just going to draw a line over and then down. And then this would be my tau p. And that's about 0.5 seconds. Okay, so we have our approximation with a dead time. So this is going to look like this. It's going to come out, have this dead time, and then it's going to trend up, and then fit this dynamic. Okay, you can see there's a little bit of a difference there again. Okay, let's go on down to the last one, or I guess it's second to last one. We have problem number 5. Now this one has some oscillation in it. So you may say, well, maybe this isn't a good approximation for this system, but let's just see how well we can do. Okay, we have delta y. Okay, and that's going to be equal to, looks like this starts down here around 4 or so, and then trends up to about 14. So it's about plus 10. And this difference right here is about 10 as well. So the gain looks to be about 1. 10 divided by 10 equals 1. Okay. Now, boy, this system is a little bit tricky. I'm just looking at where this intersects, theta p. You know, it's not, I'm going to say it's fairly negligible. If anything, you know, it's approximately 0, or you could say maybe 0.1 second, something like that. All right, and then the time constant, how long it took to get about 63% of the way there. Okay, and that's going to be about, you know, 2 seconds or so. It's kind of hard to see on this one. Might need to get out, I mean, you could get out a ruler or something like that, or you can just say, well, here's going to be my approximation. I'm going to be coming along. I have maybe just a little bit of dead time, and then it's going to trend up to this steady state value. I didn't do a very good job on that steady state value. Okay, so there is my approximation to that. You know, in this one, you're going to miss a lot of this like oscillation right here. Not necessarily a very good fit. So I'd say maybe just say it's not a good fit, or you could try to fit it to a second order system, and we'll talk about a second order underdamped system in a future lecture. Okay, let's look at problem 6. So this one, you have a step right here. Delta U is 10. And this one never quite levels off. In fact, it looks like it's unstable. So it's trending. If it continued, it might go to infinity. So this one, FOPDT, the first order plus dead time, not applicable. Okay, so for integrating processes that might you know, just come up at a constant slope, or ones that are unstable, that appear to be unstable, where it's exponential increase in that value, we just say maybe not applicable. Okay, let's look at problem 7. Wow, we keep going here. Okay, so I'm just going to do this one quickly. You know, after a while, you can just kind of look at this and eyeball it and say, you know, I had a delta y of negative 16. I have a delta u of negative 2, gain of 8. My dead time, okay, is going to be about here to here. So my theta p is approximately equal to 4 seconds, 6 minus 2. And then my time constant, I'm going to look about 63% of the way there. There's my tau p, and that's about 1 second. Okay, so we're done with this one as well. Okay, so that's just a brief overview of how to fit some of these. We've gone through a couple of these you know, systems. Some of them they fit well, some of them they don't. One of the things I've noticed in my work is that, you know, this is going to fit a lot of systems, a lot of stable systems. There's one time where I was working in a chemical plant on a reactor, and we had this reactor, and we knew that this reactor when we had an input change, we thought that the response was going to be also increasing. And when we did the step change, we saw that it actually went down and then up and then just kind of stayed at the same level. And so we had a lot of questions about why was that? We had given this step input and we got something that was non-intuitive. So we were ready to give up on, one of the options was just give up on retuning this controller. We decided to try it again. Maybe because there was a disturbance that was also entering the system at the very same time that caused that to happen. And when we did this again, then we actually got, we had very stable data coming in, and then we saw it trend up almost to the level that we expected. We were able to retune the controller and implement it, and it did a lot better. So anyway, I'll just say, these simple first order plus dead time models are very applicable to a lot of systems, and we can look at a response, a step response, and be able to characterize the system and communicate with others about the approximate dynamics of that system.